Okay, here is another video of another one of the problems that you might see on your exam. This is from exam 2 in spring 2017. This is problem number 1. Let's get started. So we have a plate with corners A and C on the x-axis is attached to a wall in the YZ plane, this plane right here, with a cable at point B and two hinges along its edge CD. So the two hinges are here. The tension in cable AB, so cable AB, is equal to F equals 140 pounds and acts on the plate at A as shown. So for part A, we want to determine the moment of the tension force about point C. And then we want to report that answer in Cartesian vector form. And then for part B, we want to determine the magnitude of the moment of the tension force about the hinge line CD. Okay, so the first thing that we want to do, determine the moment of the tension force about point C and report it in Cartesian vector form. This is where you might want to take a look at your equation sheet, or you might already know. If we want to determine the moment and we're given the force in that direction, one good rule of thumb to do is for the moment about a point O, or any point in this situation, it would be equal to the position vector crossed with the force vector. And so if we go back to our test here, let's say part A, we've got part A here. The moment of the tension force about point C, we want the moment C is going to be equal to, and then for the moment about C, we're going to want, to find moment, you're always going to want the distance or whatever from the one point that you want the moment about to the point that the force is acting on. So in this case, that means that we want the position vector to be CA. We want the position vector to be from C to A because the force is acting at A. And so we want that, and then we will cross that with the vector format of the force here, which we're given just the magnitude. We'll have to find it in vector format ourselves. So that makes it a lot more fun. So first of all, we'll just start it easier and start with the position vector from CA. So our CA is going to be equal to, if we go here and find the points, A is going to be at, looks like it is on the x-axis, so its x position is going to be 0. It is, let's see, if this is the y, its y is going to be, oh, my bad. I have made a terrible mistake. I am so sorry about that if I confused you guys. No, it is on the x-axis, so its x is going to be 6. And then in the y-axis, it's in the zx plane, and so there is no y, so that's going to be 0. And then in the z, it's on the x-axis, so again, that's going to be 0. I really apologize about that. It just kind of shows you that if you guys make similar mistakes or whatnot, I've been doing this for a while and I still make the same mistakes. So if you guys make the same mistakes, don't feel bad. They're pretty easy to make, if I do say so myself. And then we've got point B up here, which we'll need to find our force here. So point B in the x is going to be 0, this time for sure. It's going to be 0 because it's on this plane here. Its y is going to be 4, because if you take it from the edge here, looks like you go over 4. And then its z is going to be starting from the bottom here. You go up 12. All right? And then C down here, hopefully you guys could already see that, but C is at the origin, so it's just going to be 0, 0, 0. And then while we're at it, we might as well just find what point D is. So point D in the x is again going to be 0. Point D in the y is going to be 8. And then in the z is going to be 6. Okay, and so from C to A, it's just essentially going to be 6, 0, 0. And we know that because C is at the origin, and this is going to be 6. It's basically the points of A minus the points of C, so it's just going to be the 6 here. And that's all we've got for that. Now, as far as the force, this is where it gets kind of difficult, because the force, we're just given the magnitude, and we have to get it into different components here. And so this is one where we need to kind of visualize it and think about it a little harder. Now, I think the easiest thing for us to do is we get a unit vector from A to B, and then we multiply the force by that unit vector, and that should get us the force in that direction from A to B. So first we want to do the vector from A to B is going to be equal to, and this is going to be, I'm going to write this out, 0, 4, 12 minus, just broke my pencil, 6, 0, 0. And when we do that, we're going to get that is equal to, looks like, negative 6, 4, and 12. And then we're going to want to find the magnitude from A to B, which is going to be the square root of 6 squared plus 4 squared plus 12 squared. And you find the square root of that. Get my calculator on. Take the square root of 6 squared plus 4 squared plus 12 squared. And that gives us a magnitude of 14. And so that means our unit vector AB is going to be equal to 1/14 times the position vector, which, 1/14, my bad there, 1/14 of the position vector, which, if we calculate this out again, we'll do 6 divided by 14 is equal to, really ugly number there. I'm just going to go ahead and write it out in this, negative because the 6 is negative, 0.4286. We'll take 4 out of 14. Another really ugly number, 0.2857. And then 12 out of 14 is going to be equal to 0.8571. And again, just to double check, make sure that we did it right, I'm going to take I'm going to find the magnitude of all these together. It should be equal to 1. That's how I know it's a unit vector. So I'm going to take 0.428586 squared plus 0.2857 squared plus 0.8571 squared. And it gives us this value here, means it's really close to 1, means that we did the unit vector right, or that this is indeed a unit vector. And so we're not done there. Now we want force in vector format. And so that's going to be equal to the magnitude of force that we're given here times the unit vector, which is going to be equal to, it's going to be equal to 140 times all these values here. So I'm just going to go ahead and calculate that out for you guys. 140 times negative 0.4286. We get a negative 60.00I, and take 140 times 0.2857. We get about, looks like 40.00 J, and then in the K, and take 140 times 0.8571. Gives us 120 point, I'm just going to round it, K. And so we're getting a fairly clean number for the force. There were some rounding things in there. I just evened them off like this. And so that's what we've got for our force vector. And now we need to take the cross of our unit vector and our force vector. So we'll go down here. Moment about point C, as we're trying to find, it's is going to be equal to, we'll take our I, our J, and our K. And so we always want to start with our position vector. We'll take 0, 0, and 0. And then we've got negative 60, 40, and 120. And now we do the cross product. And as I've shown before, what I like to do with the cross product is I like to cover up the one that we're finding. So we're in the I direction, we're going to cover up these values and cross here. Now the thing that we're going to find out though is that when we try to cross these, we take 0 times 120 and 0 times 40. That means in the I direction, we're just going to have 0. Because normally it'd be 0 times 120 minus 0 times 40. But that's just going to be 0 times 0. And we get 0 there. Now in the J, the way I do it here is I want to cross this way and then minus this way. So when you do it that way, you always want to have a negative sign there. When we take the negative sign there, what we're going to have is we're going to have 6 times 120 minus, and this is going to end up being 0 times negative 60, so 0. That's going to be in our J. And then in our K, we're going to have, and this is going to be positive again, 6 times 40. And then we're going to have nothing when we go here again, minus 0, because it's going to be 0 times negative 60, and that's just going to be 0. So in our K. Now, what this gives us is we've got 0I minus 6 times 120 is equal to 720J plus, and then we've got 6 times 40, 240K. And then we always want to be sure and put in units as well. So as far as our units, we're going to have, it's given in pound feet. And this should be our moment about point C, our moment vector about point C. So we'll go ahead and write this down. You always want to make sure you write it in this box down here. So you've got 0I minus 720J plus 240K pound feet. Okay, and that's hopefully easy enough. And now point B. Let me go ahead and draw a line so we can separate these off. Point B says, determine the magnitude of the moment of the tension force about the hinge line CD. So we want to take this moment that we found about Z and get it along the hinge line CD. Now this is again one of those questions that I look at and I'm like, I'm not entirely sure what we do about this. So I always like to scan the equation sheet. And so if we're wanting to find the magnitude of the moment of the tension force about line CD, well, we know that we already have the moment about C. So I believe that we can use that somehow, and in doing so we can find the moment about CD. So if we take a look here at our equation sheet, we see we have vector properties here. And this is where we're going to want to use a projection down here. So for align our axes, it gives us in that, basically, to get the force or the moment or whatever vector along the line that we want, we're going to have to take the magnitude of that vector and dot it with the unit vector of the line. So that'll hopefully make a little more sense the way that we're doing it here. So we want the moment perpendicular to CD. And again, this is the moment caused by the tension force, the force F that we have here. This is going to be using the moment that we've already found about point C, because it's already acting on this line here. It's going to be equal to MC, and then for just the magnitude, we can just dot it with the unit vector CD. And that's how we're going to find the projection of this along this axis here. And so first things first is we're going to want to find the unit vector from CD. And so in order to do that, we're going to first need our position vector. And so our position vector from CD is again going to be the points of D minus the points of C. And since C is on the origin, our position vector is just going to be the points at D. So we're going to have 0, 8, and 6. And then we want to find the magnitude of it to turn it into a unit vector. And so finding the magnitude is going to be the square root of 8 squared plus 6 squared. I don't know that off the top of my head. We'll go ahead and do 8 squared plus 6 squared in the calculator, and that gives us 10. And so to find our unit vector, it's going to be unit vector CD is going to be equal to position vector divided by the magnitude CD. Now that's one thing that is also kind of given in your equation sheet. And so if it shows unit vector here, it's going to be equal to the vector divided by the magnitude. That's in your equation sheet in case you can't think about it. But when we do it here, we're going to have 0 divided by 10 is going to be 0. 8 divided by 10 is going to be 0.8. And 6 divided by 10 is going to be 0.6. So that's what we've got for our unit vector CD. And now we want to take the dot product of the moment about C and dot it with this unit vector that we found here. So we'll go ahead, force along, or the moment along CD is going to be equal to, what we've got for here is 0, negative 720, and 240. And that's what we found before. Now this is a case where on your exam, if you do get a wrong value here, you should be able to use error carry forward. And even if you got the wrong value here and a wrong work up here, you should still be able to get the work right here, as long as you recognize this fact and then use whatever value you got for the moment about C here. And they should give you hopefully close to full credit here. Maybe you might miss a point or two for getting the wrong answer, but if you do the correct work down here, you should get most of the credit at least. So we want to take that and dot it with 0, 0.8, 0.6. And so we take the dot product. This is going to be 0 times 0 plus negative 720 times 0.8 plus 240 times 0.6. Okay, and when we add that all together, get the calculator out again, negative 720 times 0.8, we'll go ahead and just put the whole thing in here, plus 240 times 0.6. And that gives us, looks like 432, negative 432. And again, this is moment, and this is already given, this here was given in pound-feet, and this here is a unit vector, so this doesn't really have units. So the units we have here is pound-feet, negative 432 pound-feet. And this was just asking in the question, it just said magnitude. So if it says magnitude, it doesn't really matter what the direction is. So we should be able to just write in our answer key here, 432 pound-feet. Okay, that's how I would solve this problem here. I hope it made sense to you guys. If you guys have any questions, feel free to email me about that. You guys know the drill. But this was question 1 from exam 2 in spring 2017. And good luck studying with the rest of your exam, guys. Have a good one.